Hi and welcome to this clip going through the Unified Chemistry 2019 paper question number 3. So this one's about an experiment that you might not have seen before. It's quite an applied question and it describes a way in which you can work out the empirical formula of an oxide of lead. So it tells you which 4 oxides of lead you've got to choose from, and the important bit of information says a student carries out an experiment to identify an unknown lead oxide, which is one of the 4 oxides of lead shown above. So it tells you there's 4 oxides of lead. It gives you an experiment that the student carries out, a diagram, and the method that the student follows. So we need to reduce our oxide of lead to make Pb as a metal. That's what the first question asks us to do. If we just bring the page down, you'll see that. So it says to write the equation for the reduction of Pb2O3 with CH4. So this would mean that either or both the carbon and hydrogen in CH4 are likely to be oxidized. So now we have to think about what the left-hand side of the equation is going to look like. So this obviously isn't balanced, but we have to think quite carefully how to balance this now. So if we look at what's happened, we can do it using oxidation numbers, or we can do it just by simple GCSE type methods. I'm going to see if I can do it with you using oxidation numbers. So I start by writing out the equation in blue, just slightly away from where the answer line is. I've already realized that there's 2 leads on the left and only 1 on the right, so I correct that. So the next thing to do is to insert known oxidation numbers. Now, the lead on the right-hand side is in the uncombined form, so that can take oxidation number 0. The lead on the left-hand side, there are 3 oxygens. Times -2 makes -6. So that must mean the lead on the left-hand side must be +3. So although 3 electrons are gained, it happens to 2 leads, so that must mean it happens twice. So I now have to work out what's been oxidized. So looking at the carbon, on the right-hand side it must be +2. So that must mean that if it's -4 on the left-hand side and +2 on the right, 2 electrons are lost. So the oxidation and the reduction have to involve the same transfer of electrons. So, going back to the reduction, we can now think about it as 6 electrons gained in total. So that must mean 2 electrons are lost 3 times. So we can start to balance the equation accordingly. So moving to the equation that's written in the answer line, I now know that 3 methanes have to become 3 carbon dioxides to support the loss of 6 electrons. Now if we do this, we now have a balancing problem with our oxygen. So we have 3 CH4s, so 12 hydrogens must mean you have 6 H2Os. If you now have 6 H2Os, you have 12 oxygens on the right-hand side. So that must mean you need to have 4 Pb2O3s on the left, which now means that the lead on the right needs to be adjusted accordingly. That means that you need 8. So this now gives us one of the answers. There's more than one possible way of doing this, dependent on what the carbon turns into. So the carbon could become carbon monoxide instead of carbon dioxide, or the carbon in the methane could become just pure carbon. In those 2 options, you'd have to do the process but slightly differently. Still using oxidation numbers, but it might not necessarily be these balancing numbers that you see on the screen. Okay, so moving on from that part of the question, we can move the page down now. So it says the student uses safety glasses in the lab coat and state with a reason one other important safety precaution the student should take when carrying out this experiment. So lots of different things you could say here, but the main thing to do is to base your answer on the fact you've recognised the risks. Now the risks come with the chemicals normally. So methane is flammable, lead is toxic. So depending on which of the two things you choose to talk about, you must state what it is that's flammable or what it is that's toxic, and then say what you need to do to minimise the effect of that risk on the student. In other words, what you need to do is state the source of the hazard, the chemical that you're talking about, the risk associated with having that chemical in the practical, and the control measure that's put in place to minimise the danger from that risk. So, the next part of the question asks you to consider 2 changes to the student's method they could make to be confident that all the oxygen had been removed. So if all the oxygen has been removed, that means that the reaction has gone to completion. So I've added to the page on this screen the student's method copied from the previous slide. So looking at it, you can see that they weigh an empty dish and then add the lead oxide and re-weigh. And then they weigh the dish and the contents at the end. So we're looking at any 2 modifications to enable the completion of the reaction. So 3 obvious ones would be to heat to constant mass, to break up the lumps of lead oxide to improve its surface area and therefore the rate of reaction, or use excess methane to ensure a maximum amount of reduction. So the next part of the question asks us to calculate the empirical formula. So let's move the page down to allow us to do this. So the first thing to do is to work out the mass of lead oxide, the mass of the lead at the end by subtracting the mass of the dish from each of the 2 pieces of data. And then finally, the difference between the 2 can give you the mass of oxygen in the lead oxide. So the next thing to do is to use that to get the empirical formula. And you do that by dividing the mass by the molar mass in each case. So if we divide one by the other, as in the mass by the molar mass, you get 2 numbers that don't necessarily add up to 2 whole number ratios. So by multiplying up by 3, it starts off as 1 to 1.33. You get 3 to 4, which gives you PB3O4 instead. Okay, so now we need to move the page down, and this particular question is simply some recall of simple structure and bonding from your first year. So it says, suggest the type of lattice structure in each of the 2 chemicals, each of the 2 substances, and it gives you the data to enable you to work that out. So first thing to do is to put down the 2 structures in terms of the lattice that's formed. Now we can put down a justification for each, explaining the difference in the melting points. And it asks you to use the types of force within each lattice structure. So silicon dioxide contains lots of strong covalent bonds requiring a lot of energy to overcome. But on the other hand, solid carbon dioxide would have relatively weak London forces between its molecules, which only need small amounts of energy to break. So hopefully this has been a useful clip. Again, thanks for watching, and until next time, see you soon.